Hi there, it's Dr. Fox here again. This is a series of 3 lessons on the AQA A-level physics course on simple harmonic motion. Now, it's worth pointing out that this part of the course is actually in paper 1. It's right on the end of paper 1 specification if you're doing your second year, your A-level. Often teachers will teach it within year 12 at the end, but it depends where you do it. It's called further mechanics. And if you're doing A-level maths, of course, you will touch upon a lot of this. But the physics is mainly around the 2 required practicals, which I'll describe in the next lesson. And the third lesson is talking about forced oscillations, natural resonance, and damping. And they're fairly short lessons to be able to do it. But there's a lot of equations, and there's some equations that are not included in the simple harmonic part of it. This is the part of specification, the first part of specification we're doing. This seems like a lot in here. But actually, once you get the concept of simple harmonic motion, i.e. the very fact that acceleration is proportional to the negative of the displacement, which is this part here, which basically means it's further away from the middle of the oscillation of a simple harmonic system, it's accelerating more. And there's some parts you've got to get your head around which are not entirely intuitive. So we're just going to go through these. Simple harmonic motion, this is just pendulums, it's springs going up and down. It may be liquid in tubes. It might be electronic oscillators as well. So basically something that has a restoring force that is proportional to displacement from the zero displacement part. And I'll show you some examples of what that means, because obviously that does sound quite physicsy. You're going to look at some graphs, some equations here. We're going to look at this cos. The mathematicians amongst you, I'll show you how you derive some of this, but you don't need to be able to derive it for the A level. Look at some graphs, then we'll start appreciating, appreciating the differences and the similarities between the graphs of displacement versus time, velocity versus time, and acceleration versus time. And then some pretty standard calculations involving this concept of omega here, the angular frequency, which I'll define down here as just the frequency times 2 pi. And this one here does not feature in the formula sheet in an obvious place, but there it is right there. It's in the wave section, so there we are. And of course, from GCSE, we've got frequency as one of the time period. Big T in here is time period. It is used as tension elsewhere, so be wary that big T there is time period. Okay, so these are our learning objectives. I'm going to just cover this top part here. These are the equations which you're going to be needing as well. So if you've got your notes out, this part here is worth writing down now and putting next to the date next to your notes so you know when you did it. And also these parts are worth writing down as well. The condition for SHM, this is it. Acceleration is proportional to the negative of the displacement. And then following on from those, all of these are derived from this one here. You don't need to know why it's the minus the square of the angular frequency, but it's worth doing. And remember, this is a constant, so angular frequency is a constant, and everything else on here, omega. I'll explain what all these equations are in a second, but these are the ones which you need to be able to do. Now, V here is velocity. That's velocity at displacement x away from the central zero displacement. And then omega appears again, and omega appears again. The big A in here is amplitude. That's the maximum displacement. So x is any displacement away from the center, and A is the maximum amplitude, which can be either side of that as well. And T there is at any time, at any point. So in other words, x could be the measurement of displacement away from the center, and T could be at any time during the oscillation. I'll come back to the required practicals in the next lesson, and then behind me there's some diagrams which I can show you later on. Incidentally, all these things down here are just taken from the specification, and therefore they're the next learning objectives for what we're going to do in the next lessons. But we're going to concentrate on this top one. Okay, so these are some oscillators, and this is the definition. It's an object subject to a restoring force of a size proportional to the object's distance from a fixed point, and so undergoing simple harmonic oscillatory motion. And of course, a simple one is a pendulum. You pull it off to one side. The restoring force in this case is gravity to be able to bring it back. And then, of course, it acts through the tension here, and it will swing, and it will oscillate. This is zero displacement from the center, and the restoring force, of course, is acting towards the center of here. So gravity here causes a tension within the string, and the tension will have a component, an unbalanced component towards the center. And of course, as soon as it swings through here, gravity then acts through the tension the other way, and then it brings it back again. So the restoring force in this case is tension of the string, of course, caused by the gravity. This here is an electronic oscillator. Take my word for it, it is. It does this type of thing. So that means that once these capacitors get full, the whole thing flicks, and these are transistors down the bottom here. This is basically what makes the world go around. This makes these type of signals. This one here, of course, is a mass spring system, where you have the restoring force on one part is the spring tension, and as it comes to the top, that tension releases, and then of course gravity causes it to be able to do it if it does go beyond it. But more often than not, it just stays within the elastic limit of that. And just behind my head here is a YouTube of liquid, and once you set the liquid going, it will go. In this case, it's got liquid 1 and liquid 2. In other words, the liquid 1 is has a different density, but it doesn't matter. You can have it with a single liquid as well. But of course, these things all wind down, and that's what we deal with damping. However, we need to, for the minute, just assume that these things are going to oscillate forever. I'll put a little star here. What's the restoring force in these examples? So in which case you can go through those and work out what's doing the restoring force in this one, for instance. Right, the SHM equations. There's a general SHM equation, which is acceleration is the negative of the angular frequency. Now, angular frequency is in radians per second, but it's radians is actually a pure unit, so it's just per second. Per second squared, of course, here, and you can see why dimensionally this works out. This is in per second squared, and this is in meters, so it's meters per second squared over here, which of course is the dimensions, the units of acceleration. And this is where you get your general system. So a general system here is a displacement x from the center. So you have your center, and then x is the distance it moves away. And at any point, at any time t, you can work out the displacement away from the center given the maximum displacement, which in this case is x0, and omega is of course our angular frequency, and t in this case is any time. So take any time, and you can work out where your displacement is from there. And of course, those mathematicians, once you will probably realize that if you differentiate this, if you do dx by dt, you get v, which is velocity, and then of course that's the differentiation of cos goes to sine, and then if you differentiate again, it goes back to cos again, and you end up with minus omega t squared out the top here, but you may have noticed that the top one is equal to the bottom one. So therefore you can substitute it in. And that's where A equals minus omega squared x. You don't need to know that for your A level, but it's worth knowing if you're going to do degree level physics. This is the type of derivation that you'd be asked to do. And of course, mathematicians amongst you, get your formula sheet out from maths, have a look at your trig identities, and you'll be able to see that why that is the case down there. But that can be a bit of fun, bit of homework for you. I'm not going to dwell on it. Okay, so YouTube's full of great videos about this. I've nobbled one here. This is a good one that I show, so if you can type that in quickly or take a snip out of it or go and see that, or just basically type in simple harmonic motion views. Now, the reason I'm showing you this, you need to view ones where you've got displacement x, you've got velocity and acceleration. I'm going to show you one in a second, but this is part of the specification. You have to know what each one of these is related to the other. And the reason I mention this is because on the previous slide, I showed you that if you differentiate x, you get v. What differentiate means is just take the gradient at that particular point. So if I take the gradient at this particular point here, I end up with this value here. And you think, oh, hang on, that's a negative gradient, isn't it, there? Oh, yeah, that's a negative gradient. That's a negative value, see? So if I take the gradient of here, I get this value. And if I take the gradient again, so what's the gradient here? Oh, it's still negative, isn't it? There you go. It's still negative. Now, there's different shapes in here, of course. As when it gets down to here, my gradient is its maximum here. And this is when my velocity is its maximum negative value here. And then this, of course, is when my acceleration is 0. Now, let's think about that for a second. When the acceleration, so when the displacement is 0, my velocity is maximum. That makes sense. That's when the pendulum is coming through the central part. so the pendulum is coming through. It's its maximum velocity when it's passing through when the displacement is 0. What's the acceleration? The acceleration is also 0, which you think, hang on a second, it's moving. But this is the case where that's the only place it's going at constant velocity, instantaneously, of course. It's going at constant velocity. The moment it passes through, it goes through from one side through to the other side, it'll start decelerating, and they'll get to a point where the velocity is 0, where it's its maximum displacement. And of course, that's where you get it here. You've got maximum negative displacement, you've got 0 velocity, and you've got maximum positive acceleration. Why? Because the acceleration is acting towards the center of here, either end. It's maximum acceleration. Here's the concept point that's really tricky for A-level students. Your maximum acceleration is when it's not moving. And that is probably the hardest point to get across. The maximum acceleration is when it's not moving at either end of the oscillation. So if it gets to either end, it's not moving, maximum acceleration. That's when students go, well, how can it be accelerating? It's not moving. Very easily, look at simple harmonic motion. The maximum acceleration takes place at each end, and it's the negative of the displacement. In other words, displacement is measured from the center outwards. So that means your acceleration is this direction if your displacement is measured in that direction. So there you go. It's a strange one. You have to think about it a bit more, and this makes it a little bit clearer. Okay, so imagine a mass spring system here. So you've got your displacement away from the central part. So imagine you've got a spring, you just pull it, and it just goes up and down like one of those children's toys. If your displacement is maximum, you can see your velocity is 0 and your acceleration is the maximum negative value. If your displacement is 0, you've got the maximum velocity and you have a 0 acceleration in the center. It's going constant velocity. And then, of course, on the converse, when you've got maximum negative displacement, you have 0 velocity, but you have maximum acceleration in the opposite direction. Note that these are the negative of each other, and this is the pi shifted value on here. Sorry, pi by 2 shifted on here. This is essentially the sine wave, this is a cos wave, and this is back to a sine wave again. And at the bottom here, I included the idea of KE and potential energy. Systems being a thing. And really, KE traces velocity, as you'd expect. Potential energy traces your displacement, which makes sense because it's gravitational potential energy and kinetic energy being constantly interchanged in this case, but it depends on it. It's pendulum, it's slightly different. But as you can see, everything is positive here because energy is always positive, including these potential energy values here, and they're constantly interchanging. Worth looking at that diagram for a while to be able to really work out what's going on. I'll show you some questions in a minute of how this gets asked, because this is all well and good. If you don't do an exam question, it's not really worth just looking at. There you go. So look at them, nice and relaxing. Displacement, velocity, acceleration. This is the gradient of this. This is the gradient of this. Rewind the video, have a good look at that to make sure you understand the relationships between those. Now, one really good way of being able to work it out is that if you basically put all these together. So at time t0, in this case, we've got our spring system we put on a side here, actually, which is probably better because you don't get gravity complicating things. So this is a spring. If you stretch it, it'll restore, and if you squash it, it'll restore. So this case, we're just starting off at A max, minus A max, which is the acceleration. So it's maximum displacement. So in this case, the position is x max, maximum displacement off to the right. Velocity here is 0 because it's at the extreme, minus A, and k equals 0 because the velocity is 0, and p equals max. And then, of course, if we go to a quarter of the way through here, position is 0. So this is at the 0 displacement. Maximum velocity, 0 acceleration, kinetic energy max because the velocity is maximum, and of course your potential energy is 0. Halfway through your thing, so it's got to the other end, minus displacement, 0, A max, 0, Pe max. Why is it 0? Because the velocity is 0. And then, of course, you can try filling these things in here to make sure you understand how each of them are related to each other. So stop the video, in your notes, try doing that table here, and then, of course, we're going to try and do the whole thing from memory. So just do those bits on here. This is just the displacement on the way back, and this, of course, is exactly the same as where you started. So it should be fairly easy. Once you finish that, then we'll go on to the next one. 3, 2, 1. I've taken lots away. Try it again. Do it in pencil. Importantly, the top one is the same as the bottom one. You need to know these three important parts in between. So position, V, you should be able to work it out from this. And then I'm going to go on to the next one. 3, 2, 1. And there's the answers. Then, of course, scribble the whole thing, do the whole thing from memory. It's really important you appreciate the links between these, but also you can immediately say maximum displacement, maximum negative acceleration, the velocity 0. Of course, Dr. Fox, why are you even asking me? Ask me about potential energy. Potential energy is, of course, it's the maximum because the velocity is 0. Don't stop being so patronising. That's what you need to get to a stage 2. Okay, so here we go. We've got some multiple choice questions I've dug out here. And I've given you some clues at the top here. Which one of the following graphs shows the acceleration A of a body with moving simple harmonic motion varies with its displacement x? So which one of these we're looking at? Now, first of all, whenever you try and work out a variation, you should go to your formula sheet and have a good look. Condition for SHM, A is proportional to minus x, and there's the defining equation on here. Got to be this one. But the question is, why is it this one? Why is it not this one? You see, this here is trying to get students to believe this, but this, remember, is a constant. I don't care the fact that it's omega squared. It doesn't matter in the slightest, because this is a constant, even though it's a constant squared. Then we've got this one here. Again, mathematicians and what you might think, yeah, simple harmonics promotion has probably got something to do with circles, isn't it? Yeah, get drawn in. And then this one will probably get drawn in the fact that there's, they're directly proportional, there's a straight line in there, but this is the only one with a negative relationship between A and X, so it's got to be D. You can see why they're doing it. Remember, multiple choice is trying to trick you. That's why they put the other answers there, to make sure you're thinking about it properly. Okay, now we've got other questions here coming up. Questions 1 and 2. I've included all of the equations you need at the top here as well to be able to complete these. And you can see there's a whole raft of them. And really, this is an exercise in exam question diagnosis. I'll talk them through, and this is how you do an exam question. A baby bouncer, consisting of a harness and elastic ropes is suspended from a doorway. When a baby of mass 10 kilograms is placed in the harness, the ropes stretch by 0.25 meters. When the baby bounces, she starts to move with a vertical simple harmonic motion. What is the time period of her motion? So, time period of a motion, we've been given a mass, we've been given a stretch there, but then when the baby bounces, it starts to move here. So there's quite a few stages. For 1 mark, this is quite a lot of work. So for instance, this is a mass spring system. We're not being given too much about any, we've been given this displacement here, but we're placing the baby in, and then it starts to, she starts to bounce, my apologies. So therefore, we have to use this mass spring system to start off with. Okay, but we still got K. We can work out K though from an equation that you should know from GCSE. Force equals spring constant times extension. Now, force, of course, they're trying to get you to be tricked out by this. Force, of course, is the weight, which therefore is 10 times G. So 10G is your force equals the spring constant, which is what we want, multiplied by this value here. Get your calculator out. Get the spring constant first. Then, of course, once you've got the spring constant, this is your time period here. You know the mass of the baby. You've just worked out the spring constant. Stick your numbers in, and you should end up with those values on here. Okay, so there you go. Total mark 1. Which one of those is it? Which one of the following statements is true when an object performs simple harmonic motion about central point O? Oh, incidentally, I'm going to give you the answers in a minute. I'm just going to do these first. Which one of these statements is true when the object performs simple harmonic central point O? So here we go. This is where you have to concentrate. Trues and falses in an exam pressure situation. The acceleration is always directed away from O. Always directed away from O. The acceleration and velocity are always in opposite directions. Velocity, always in opposite directions. Hold that one. Let's come back to that one. The acceleration and displacement of O is always in the same direction. Negative sign. The graph of acceleration against displacement is a straight line. That sounds suspiciously right. Let's read this one again. The acceleration and velocity is always in opposite directions? Are they always in opposite directions? Have a think and come back to it. Okay. Right, question 3 here. A body moves with simple harmonic motion of amplitude 0.5 and a period of 4 pi seconds. What is the speed of the body when the displacement of the body from the equilibrium position is 0.3 meters? So a body moves with simple harmonic motion at 0.5 amplitude A, period, that's T. What is the speed? That's V of the body when it's right. So we've been given a displacement here. So we've got to be using ones where we're given a displacement away. So really, we could be talking about these. It's not talking about maximum speed, is it? Because we've been given an amplitude. So it must be one of these. So just have a quick look. Velocity, that's what we want. Omega, we can get omega because we've got the period and we can work out what it is from these two equations here. Hold that thought. And we've been given amplitude and we've also been given it's this one here. Okay, now what I'd like you to do is you've got to do a bit of calculation instead of just listening to me, which is we've got to work out what omega is. Now we've got 2 pi f. So omega equals 2 pi over t. Really, really important equation. Omega equals 2 pi over t. It's not given in your formula sheet, but you need to be able to know it. So just stick 4 pi, 2 pi over 4 pi. I think you can do that in your head. And therefore you've got your velocity. It's plus or minus, of course, because it can be either end and going in either direction. Omega, you can stick it in now. You've got it. A, of course, is the amplitude, which is that one there. And x, of course, is your displacement. And then you work out which one of those it is. Go and do that. Next one. Time period of oscillation is a simple pendulum length L, and is the same as the time period of oscillation of M attached to a vertical spring. So we've got two systems here. We've got one where there's a pendulum swinging, and another one where a mass is going up and down. The length and mass are then changed. Which row A to D in the table will give a simple pendulum with a time period twice that of spring oscillations? So therefore, you're looking at something. You're keeping this. You're keeping one the same, and you're trying to move something else. And these are the ones where the examiners really love these algebraic ones. I think most of us are comfortable with the first few that we've done. But then when we start doing things in algebraic sense, you need to read them very carefully. I'll leave you to read that one rather than me reading it out now. I'm going to read it out again, but it's worth reading it, pausing the video and trying to work out which one it is. But I'm going to go through it again. So if you want to pause the video now, I'm going to read it out again with stress. The time period of oscillation of a simple pendulum of length L is the same as the time period of oscillation of mass M attached to a vertical spring. The length and mass are then changed. The length and the mass are then changed. Which row A to D in the table will give a simple pendulum with a time period twice that of the spring oscillations? So the pendulum is now going twice, as it were. So the time period is twice that of the spring oscillations. Look at these two equations here. So I need the pendulum to be twice the length. So pendulum is proportional to the root of length, and the time period of the mass spring system is again proportional to the root of n in this case. So which one of these is doing this way? So in this case, you're increasing both of them. It's not going to work, is it? If you're increasing both, then you'll get both going on. So if you double the length and halve the mass, sounds about right, doesn't it? So I'm doubling the length because that means that the period will be longer. If I halve the mass, is that going to work? Let's just hold that thought. If I halve the length and double the mass, is that going to work? Half the length, half the mass. Are they keeping them the same? So that's not going to work. So it's between these two. I'd like you to think about which one of those it is. You can stick the numbers in here if you like to which ones you're going to get, but you can work it out. Okay, last one with this, and then I'll give you the answers. A body moves with simple harmonic motion of amplitude 0.9 and a period of 8.9. What is the speed of the body when its displacement is 0.7 meters? So let's read this again. A body moves with amplitude A, period, big T. What is the speed of the body when its displacement is 0.7? Speed, displacement, amplitude, period, boom. Now, I've purposely taken away those equations that you need to be able to have on the tip of your tongue, to be able to do it, because you've got to work out omega in this case. So it's this one here. Okay. Now, if you get this a question and they give what's the displacement at time, then therefore you just leap to this one here. That'll give you displacement, of course. Very typical type of question, but keep it all in mind. And then if you ever talk about maximum speeds or maximum accelerations, you've got those two equations in your back pocket. It's just basically equation management is this part here. Okay, so there you go. Get the equations out and I'll come up with the answers. So it's A, D, C, B, and C with the answers. You need to rewind the video, have a look, come back again, check you got the right answer, come on and check it. So pause that now and then go on because I'm nearly done. And there we are. So we looked at the characteristics of simple harmonic motion. There's the condition, remember that the relationship is the negative of the gradient. Defining equation, and then of course these two other equations which are related and how you work out different parts of the simple harmonic motion. Graphical links, we looked at that, animation, and of course the gradients which link displacement to velocity and velocity to acceleration. And then these maximum speeds. There are quite a few other questions involved. There's not. They're usually in paper 1 of A level. So go and look in those because they're always scattered around in there. I'm only giving you a few examples here. Physics and Math Tutor have got loads. They're all split up. Go and do all of them. It's a straightforward, really good website. Okay, I'll see you next time.